So homework number 2, that is due today, and let's look at some of those answers. Question 1 says complete the table, and we're looking for the number of neutrons and the mass number. The mass number for the two isotopes is of course the larger of the two numbers given for each element, because mass number is neutrons and protons. So the mass number here for the oxygen is 17. The mass number for the titanium is 49. For the number of neutrons, the mass number is protons and neutrons, and the atomic number below, 8 and 22, is just the number of protons. So the difference between the two is the number of neutrons. So we have 9 neutrons plus the 8 protons to make a mass of 17. And in our second example, the mass number 49 minus the atomic number 22. So the number of neutrons is 27. Now to define isotopes in question 2, of course the isotopes have the same number of protons or the same atomic number. That stays the same, but it's the number of neutrons which changes, which also means the number for the atom's mass changes. So isotopes have the same number of protons or the same atomic number, but different numbers of neutrons, which leads to a different mass. And that gives us isotopes for the same element. So given a question with different isotopes in question 3, and to work out the abundance average mass, we're going to take the relative percentage of each mass number and add them together. So for the first one, we want 20% of 245, which is 49 units of atomic mass, 42% of 246, which is 103.32 AMU, 7% of 248, which is 17.36, and 31% of 252, which is 78.12. Add them together, and the average abundance mass for this isotope is 247.8 atomic mass units. Remember, your average has to be higher than the lowest mass, but lower than the highest mass. Otherwise it can't be an average. An average based on the relative abundance. Question 4, which is looking for the electron configurations. Remember, the shape of the periodic table is telling us about the kinds of orbitals we see and the order that the subshells appear. So every time we're on the left hand side of the table, we're talking about electrons going into an S subshell. Every time we're on the right hand side of the periodic table, we're talking about the P subshell being filled. And every time we're in the middle, in this middle metal block, we're talking about the D subshell being filled. So for boron, 1 S2, 2 S2, 2 P1. Calcium, which is the second element in the fourth row of the periodic table. Remember, from the shape of the periodic table, we can see that calcium has 3 shells which are already complete. 3 shells complete, just like argon at the end of the third row of the periodic table. So we can write argon in square parentheses, and we're saying that the configuration of calcium is like argon, but then goes beyond it with those 2 electrons in the 4s subshell. Or we could write out the entire configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But we are allowed to write argon in square parentheses to say that the configuration of calcium is like argon, but goes beyond it with another 2 electrons. Likewise, copper can initially be summarized as being like argon, but goes beyond the configuration of argon with 2 electrons in the 4s subshell. And for the 3d subshell, remember it's 3d because the d is one behind the 4s and the 4p. The 3d contains 9 electrons in that d subshell. So we want to correct the configuration for iron, which is in the middle of that D block of the periodic table. So, first mistake here is the fact that we're starting with the 1s subshell, but our configuration claims it's a 2s. So 1s2 is the first subshell we see. Then we see the 2s with 2 electrons. Our second mistake is in the next subshell listed. The 2p, of course, with just 3 orbitals, can contain a maximum of 6 electrons. So that should be 2p6. We then go on to the 3s and then the 3p. Again, it should be only 6 electrons in the 3p. We then move on to the 4th layer of the atom. And of course, we see electrons put into the 4s subshell before electrons are put into the 3d. So the 4s subshell comes first, then we see the 3d. Although it's part of the 3rd shell, we don't put electrons into that subshell until we've added electrons into the 4s. And instead of being 3d 9 electrons, the correct configuration for iron would be with 6 electrons. And that gives us a corrected configuration. We have the 1s, the p subshells can only take 6, and the 4s is filled before we start filling the 3d, and it should be just 6 electrons in the d instead of 9.